Thanks again to everyone who's able to join us live and take the time to participate in this. I want to welcome each and every one of you. If you have any questions during the webinar, feel free to submit those via the chat feature, which should be off to the right. You can click on that, and myself and some others will be answering some questions as we have opportunity during the presentation. And then afterwards, we will have a dedicated time for Q&A where we can delve into a little more depth. So looking forward to starting with you, and thank you again for joining us. Welcome to the Preferred Utilities Fuel Oil System Equipment and Design Overview. I am Alex Canney, and I'll be presenting to you today as well as participating in the live chat question and answer time afterward. For more information, you can always find us at Preferred Utilities website, preferred-mfg.com, or feel free to just give us a call. Today we're going to be going through several different parts of the topic of fuel oil system design, focusing primarily on how to start a new design and where to go from the beginning. Here on our agenda, we're going to be starting with an introduction to the company, which I know some of you are already familiar with. We're going to be taking a brief look at a fuel oil system overview, and then we're going to be spending some time on a design example. Once we've taken a look at our design example for both the amount of fuel in the system, how fast the fuel is moving throughout the system, etc., we're going to take a look closer at some critical components in the system and what's necessary for a good design. Finally, we're going to be taking a look at some fuel oil system controls, as that part of the system is very important, more than just the hardware. And then at the end, we have a section with some fuel oil quality considerations that we're not going to take time to walk through today, but it is a resource that's available for future use and something that we can reference if there are any specific questions about fuel oil system design that impact fuel oil quality considerations. Preferred Utilities is a family-owned company operating continuously since 1920. We are a very engineering-heavy manufacturing company with over 180 years of combined engineering experience, which is probably a low estimate. Our headquarters and factory are located right in Danbury, Connecticut, and we tend to focus on projects and applications for mission-critical facilities. So that's going to be things like hospitals, data centers, production facilities that just can't go down. Now, we do have offices all around the country, all the way out to California and down to Texas. The material that we're going to be covering in this webinar today is going to be focused around the Northeast. I am the Northern New England Regional Manager for Maine, New Hampshire, and I also assist with Boston. And most of the material that we're going to be covering today is going to be applicable to the Boston area. So, with every fuel oil presentation, I like to start with a brief system overview. Not everyone has designed a fuel oil system or part of a fuel oil system recently, and so it helps us to get an idea of what we're talking about when we talk about the system. So on this slide, you can see, starting from the lower left and then working our way to the right and upwards, we have the way the fuel oil system would be historically or traditionally designed. On the lower left, we have a bulk storage tank, which in this case is below ground and outside the building envelope. And the delivery truck would pull right up to this tank and deliver it through the fill connection on the left. This tank would have level monitoring, leak monitoring, etc. And it could be within the building, it could be outside the building, it could be above ground or below ground. Following the fuel as it moves throughout the system, we next have our duplex transfer fuel oil skid. And you'll see we have two transfer pumps on there, which is very typical for a mission-critical application, where one pump is sized for the full function of the system, and then the other pump is a lag pump or a backup if there's any issue with the first pump. Following the fuel from here, it goes up to the generator, and it is filling a day tank or a local storage tank at the generator itself. And we're going to be taking a closer look at each part of this system and how we would size each one of these components, as well as the piping and valving. Now, directly to the right of the duplex fuel transfer pump set, we have another important piece of the system, which doesn't necessarily transfer fuel to the generator, but it does maintain the quality of the fuel in the system, and that is our fuel polishing skid. Now, I like to refer to this as a fuel polishing skid rather than simply a filtration skid. We're doing more than just removing particulate from the system. We're also removing water, which is the largest driver of fuel oil quality degradation for stored fuel. So when we talk about a traditional fuel oil system, it's going to be similar to the setup we see here. There may be more day tanks at the generators, multiple generators. There may be multiple main tanks even, but typically we're going to have a large amount of fuel stored in one place, and then that fuel is going to be moving to another place to serve the generator itself. And the bulk of what we're talking about today is going to be applicable primarily to emergency generators, as that's the application that we're seeing in mission critical facilities. Some of this could also be applicable to fuel systems that serve boiler plants, but that's not the primary goal of this presentation today. So let's take a look at a fuel oil system example. If we have a new project, where do we start? And how do we get the ball rolling from a blank piece of paper if we have a project? Typically, the way that we're going to walk through a design is we're going to begin with the amount of fuel needed in the entire system, and this can be dictated by the owner, by code, or insurance. Then we're going to take a moment to size the day tanks themselves that are local to the generators, and that'll give us the size of the tanks in our system. Then we take a look at how quickly the fuel needs to move throughout the system, sizing the pumps, and that's going to be based on the consumption rate of the generators, with a very important caveat that we're going to take a look at. And then finally, we would size the piping and the valves in the system based on that previously calculated fuel transfer rate. So, starting from the beginning, we have our desired runtime. In this example, we're going to take 72 hours, which is a typical amount of runtime for a mission-critical facility. And then we're going to take a look at what is actually burning the fuel. For this example, we're going to say that it's 4 2-megawatt generators, which is a fairly large plant. And then we can use a general rule of 7 gallons per hour per 100 kW of capacity for the generators. And this general rule, the nice thing about it is it's not very dependent on the model or the make of the generator. It's going to be a good rule and generally conservative across the board. So doing a little bit of math here, we come up with our total consumption by the entire plant, assuming that it's fully loaded and that there's no redundancy as far as capacity, and we have 560 gallons per hour. Now, if we multiply our burn rate by our total runtime, we get a raw number of 40,320 gallons. And the important thing to understand here is that this is a raw number. Now, we have some tools that we can use also on our website, preferred-mfg.com, to find out how much fuel you need in your system. Now, we're going to take this raw number, and there's some considerations that we need to add to it. Understanding that we need a certain volume of usable fuel, so we wouldn't run out and specify a 40,320 gallon tank right on the nose. We need to account for ullage and drop tube gap to start. Now, ullage or ullage, depending on how you pronounce that, is the amount of headspace on the bulk storage tank that can't be filled with fuel. We don't want to fill all the way up to the very top. Drop tube gap is going to be the amount of fuel at the bottom that can't be pulled out because the drop tube for the suction side of our fuel transfer system doesn't go all the way to the bottom. Now, that is by design. We're going to take a look at why that is in some future presentations talking about fuel oil quality a little more closely. But basically, at the bottom of the tank is where a lot of the sediment and the water are going to live. And our polishing system would want to be able to access that, but the transfer pump set would not. So we have an adjustment for that. And let's say we add 10% for ullage, 10% for drop tube gap, an additional 5% for testing and exercising the fuel. Again, this is a 40,000 foot look here at the beginning. We're basically just trying to wrap our understanding around the general sizing of the different components in the system. So that would come up with, let's say, 125% of that raw number. Now, NFPA in 2016 now calls for 133% of design runtime to account for testing, so we would bump that number up to 133% of that raw number. And we'll round that figure to a nominal size, and that would be what we would base our bulk storage tank sizing on. Now, that selection could also be modified depending on how large the day tanks are in the system. For a typical single day tank, single generator system, we wouldn't necessarily need to factor that in. But if we're looking at a system with multiple generators, multiple day tanks, we may want to take the size of those tanks into account when we're sizing the total amount of fuel in the system. Now, of course, we're going to take a closer look at some of these components later. Right now, we're just talking about sizing, but it is important when specifying or selecting a main tank. Obviously, any of the connections that are available that we are designing, that the sizing, the number, that's all very important. And we're going to take a closer look at some of these components in a little while. Now, moving on to day tank sizing. Again, this is the tank that's located at the generator, sometimes called a belly tank, depending on its size and location and configuration. And we're going to take a closer look at the tank itself and how we would select and design it. But right now, for the amount of fuel that we need this tank to store, it's very important because this is the tank located at the generator. If there's a failure in the transfer system or problem with the piping and valving, etc., in the rest of the system, this is the amount of fuel that the generator has immediate access to. So we want to give ourselves some time if there's a problem with the system and power is down to be able to address that problem. And ideally for life safety or mission critical applications, we're going to be looking at 2 to 4 hours of generator runtime from that day tank. Now obviously more is better, but we're limited typically by local codes on how large that can go. Now here in Boston, historically we were requiring 60 gallons or less for the local tank, and thankfully that has changed, and they're now allowing a tank to be sized 2 to 4 hours if it's based on a life safety system. And this allows the size of that tank to scale with the generator itself. But ultimately, no matter where you are in the country or what application you're looking at, the final say is always going to be determined by the local fire inspector or local building codes. And we'll take a closer look at how that happens here in Boston. Just a general overview, we have 2 basic places that these codes are going to originate from. We have our local building codes, and then we have some considerations from federal law as well. And our local building codes are going to come down to things like UL listing for equipment, NFPA for best design practices, maybe some flood resistant construction requirements, things like that, that are modifications and references from the International Building Code. Now, if we were to ask, depending on the question, for instance, if we have a tank, what should it be constructed from? Well, UL or NFPA might give us an idea of the construction requirements, but if we're asking the question, how far can the tank be located from the wall or how close, that would be something that may be dictated by federal requirements such as OSHA. So those clearances would come from there. So there are many different places that we would go to answer questions for the design. Now, out of all of those codes, most of our time is going to be spent in the National Fire Protection. And when we look at the NFPA codes, they go from NFPA 30 generally up to NFPA 110 for systems that we're talking about right now. And they go from more general to more specific. So we have some requirements in NFPA 30 that is generally about stored combustible liquids, but they may be superseded by NFPA 37 or NFPA 110. So if we see something in NFPA 110 that's different than NFPA 30, it's going to be more applicable and take precedence over the previous requirement. And NFPA 110 is the code that we're going to spend the most time in if we're answering questions about mission critical backup power systems and how to design the fuel oil systems for those. Now we've taken a look at how much fuel is being stored in the system, both in the bulk storage tank as well as the tanks that are local to the generators. And the next point that we need to design are the pumps. We need to take a look at how fast does this fuel need to move from one point in the system to another. And typically worst case is going to be used for consumption. We want to assume that generators are fully loaded, that all of the generators are calling at the same time. Now a single pump would be sized about 2 to 3 times the total burn rate depending on the size of the system. Flow limiters can be used to restrict the flow into a single day tank when multiple day tanks are used. If for instance we have a setup where we have a single duplex transfer pump set and 10 day tanks, and we're sizing for the consumption of all 10 generators running at the same time. In a real-life situation, often only one day tank inlet valve will be open and calling for fuel into that day tank. So we don't necessarily want to supply 10 times the flow rate into that one, which will require us to upsize all of those valves, as well as any return pumps that are associated with that day tank. Now, one of the advantages of using positive displacement pumps, which is the standard for our transfer skids and recommended by International Mechanical Code, is that they have the advantage of being almost constant flow that doesn't depend on the back pressure in the system. So if we're looking at a system in the design phase, we may not know exactly how many valves are in the discharge side of our transfer pump set, how much piping, how many elbows, etc. But we know that our flow rate is going to be fairly constant, and we can design based off that. Now, one of the caveats that was mentioned earlier was our general rule of 7 gallons per hour per 100 kW, and that there is a case where flow rate may change depending on this special case. And that's if the return from the generator goes to the main tank rather than back to the day tank. And this can cause several issues, and we have a slide here that shows our typical piping arrangement where we can follow from the main oil tank. The fuel goes into our transfer pump, up our supply, and then supplies into the day tank. And we can see that the emergency generator in blue at the top right has its supply and return within the day tank itself. So any fuel that's not being burned is going to circulate right back into the day tank. Now, most generators, almost all that are on the market right now, will circulate more fuel than they're actually using. And one of the things that we're finding in the field is that the amount of fuel that they're circulating is fairly significant. It can be 2 to 3 times the amount that they're actually burning. So if we go to an alternate piping arrangement, some of these rules that we talked about no longer apply. So in this arrangement, as you can see on the top right at our emergency generator, the return line does not go directly back to the day tank. It goes all the way back down to the main oil tank. And if we have this piping arrangement, which I've seen in the field, sometimes it's done because hot fuel is being returned to a very small day tank and can cause the system to trip out on high temperature. It could be just from the way the contractor decided to do the piping. The problem here is that now we need a supply pump that is much larger than what we had before, because the onboard pump on the emergency generator itself is circulating 2 to 3 times as much fuel as the actual burn rate. So that needs to be supplied. Now, if we're in the design phase, this can throw an additional monkey wrench into the equation, because we don't necessarily know early in the design what the flow rate of that onboard generator pump is. We'll know the kilowatts or the megawatts rating that we're designing, but we can't use our general rule of 7 gallons per hour per 100 kW anymore. Even though the consumption is known, the total circulation is not known. And with this piping arrangement, that is the factor that we need to design from. So it's an important note to take and an exception to some of the rules that we laid out. Taking a look at the piping now, we have the amount of fuel in our system and we have how fast it's moving. And now that we have that general flow rate, we can start sizing things like piping and valves. Now, when we take a look at our system, if we remember the overview we looked at earlier, all of the piping that's in the system, even though the piping between the main tank and the transfer pump set may be the shortest run of piping physically in the system, it is going to be 90% of the consideration for designing and troubleshooting in the field. And that's because with positive displacement pumps that are quote-unquote self-priming, that section of piping will generally be under a vacuum, whereas the rest of the system will most likely be under positive pressure. And if you've ever worked with any sort of a hydraulic or hydronic system, something that's under a vacuum can pose a lot of issues. Now, one of the things that we want to do right off the bat is we want to make sure that we're not undersizing any of the valves or piping on that suction side and presenting too much of a restriction to the transfer pumps. And it's not just about the size, it can be about the location as well. So when using gear pumps, we want to make sure that our suction value is limited to about 15 inches of mercury vacuum or less. Now, the actual net positive suction head required and available may vary by manufacturer, but these general rules are going to be safe no matter what equipment we're using. Typically, we're going to be seeing about 5 inches of friction loss in the system, and this is determined by the size of the piping, the size of the valves, etc. That will generally leave us about 10 inches of mercury for static lift, which translates to about 12 feet of oil. So that means right off the bat, we know if we have the worst case scenario, which is fuel low in the main tank, 12 feet lower than the suction of our transfer pump set, that's pretty much our limit. If we go any lower than that, any more vertical distance, and we're going to have some trouble. Now, we do have a very useful online sizing tool available at our website, preferred-mfg.com, that we're going to be previewing here in another week and running through and showing you some examples. And it's a very powerful tool that allows us to do exact valve counts, elbows, pipe sizing, and see and predict what those values are going to be for the design phase. But these general rules are going to get us started. Typically, depending on the manufacturer and the actual pump head being used, going beyond 20 inches of mercury is in the range for cavitation. We want to stay away from that. Now, the last part of the system that we need to size is the discharge pipe, and that's the pipe from the exit of the duplex transfer pump set all the way up to the day tank. And the nice thing about this is, since it's under positive pressure, we have a lot of leeway. We're not just working with a very limited range of pressure here. If it's a high rise, we can do 100 psi, 200 psi, or more, whatever's needed. But we do want to be within reason. So we're going to size based on worst case scenario and understanding that the fuel flow needs to exceed the consumption. And we did those calculations. Now, historical requirement was that the fuel velocity not exceed 7 feet per second. This was primarily based on the fact that diesel fuel can foam, but really, while we keep that in mind as a general rule, one of the most important ways to keep diesel fuel from foaming is to make sure that on the supply side of our system, anytime we're putting fuel into a tank, whether it's the main tank or whether it's a day tank, that we have a dip tube that drops that fuel down below the surface of the fuel that's already stored in that tank. So we're not just cascading fuel into the tank and causing that foaming. Now, for our return pipe that comes from the day tanks back down, we will generally go one size up. So if we have, for instance, 3/4 inch supply piping, we'll do a 1 inch return. Or if we have 1 inch supply, we'll do 1.5 inch return, and so forth. Now, I'd like to take some time to look at the critical components that make up this fuel system a little closer. We talked about how to size some of these components, but we need to take a look at the qualities that these components have themselves and what are some of the minimum requirements for a mission-critical fuel oil system. Taking a look at the heart of the system, the pumps, there are really two different types of pumps that can be used for fuel oil applications. We have turbine pumps, which are commonly called submersible pumps, and then we have gear pumps, or positive displacement. Now, the primary difference between these two is that for the submersible pump, they are going to be a high volume output for the same horsepower, but they are very limited on the amount of pressure that they can have. For a positive displacement pump, they're typically going to be a lower flow rate for the same horsepower, but they are going to have a very flat output versus back pressure curve and going to go to a much higher pressure. Now, these are going to be necessary for high-rise jobs or remote fills, any application where we need a large discharge pressure. And the nice thing is, as we said before, that flow rate is going to stay fairly constant even if our output pressure does increase. Now, with the submersible pumps, one of the advantages is that having a relief valve is not as necessary, and this is an important safety consideration for our positive displacement pumps, where if someone was to deadhead the discharge, we need to make sure that we have relief valves that are going to discharge that excess fuel and relieve the pressure. And one note that I would make here, when we're talking about critical safety components, there are two different styles of relief valves that can be used on a system. There's the internal relief, which is installed directly in the pump head, and then there's the separate relief valve, which is piped onto a skid. The separate relief valve offers an advantage because if we were to deadhead this pump, it is still going to flow fuel through the pump, through the discharge, to the relief valve, and then the relief valve would divert that fuel back to the main tank at low pressure. With an internal relief valve that's installed in the pump head itself, it merely circulates a very small amount of oil from the discharge right back to the inlet. And this small amount of fuel is not going to be useful long term to continue to lubricate the internals as well as maintain a proper operating temperature. So in this case, an internal relief valve may not be appropriate for the transfer pumps, but you will see it on things like the polishing skid or return pumps at the day tank that aren't necessarily as critical for providing fuel to the generators themselves. Now, the package pump set offers a lot of advantages, and this is going to be typically how we see these in the field now. There are still some applications where we'll see the transfer equipment being designed piecemeal, and the contractor will purchase each part, such as the strainers, the gauges, all of those different things. But the advantage of having one manufacturer or sole source of supply for the skid itself is that necessary safeties, such as the relief valve that we just talked about, all of the gauges, the strainers, things like that, are all going to be sized right from the get-go properly. Whether it's a safety or whether it's just a pressure drop across the strainer, all of that is going to be coordinated at the factory and can be required to have a factory test to make sure everything is working before it shows up at the job site. And that includes the controls as well that we're going to take a closer look at later. Moving throughout the system, another critical part of the system is the remote fill port. So this is the part of the system that the fuel oil delivery person is going to be interacting with. They're typically not going to have access to the main tank itself or to the other controls. So this is the part of the system that's going to indicate to them any sort of alarm conditions like high level in the bulk storage tank that they're going to need to know about. And these can be installed in ground, in wall. They can be set up for gravity fill or pumped in fill. Now, the important thing to note about this piece of equipment, at a minimum, what we should be looking at is an audible and a visual alarm. And the audible alarm will come on immediately once high level is reached in the main tank to indicate to the fuel delivery person that they need to stop providing fuel to the tank. The visual alarm, however, will not silence after the 30 seconds or after acknowledgement by the fuel oil fill person. That will stay on. So if somebody shows up 30 minutes later to supply an additional amount of fuel, they'll see a sign and an indication that says if this light is on, the tank is already full or already in high level. The next component we're going to take a closer look at is the day tank. And this is one of the most important parts of the entire system. As we mentioned before, this is the part of the system that provides fuel to the generator should the rest of the system fail. There are many different styles, sizes, and shapes. We have here two examples off to the right. On the top, we have a traditional day tank that would be used in an indoor application with an open rupture basin. This allows easy testing of the interstitial leak. And then we have below that a picture of a belly tank, which is one of our more modern designs that we're seeing more and more of. As you can see, it's a bit shallower and larger, and it has an enclosed secondary containment. Now, when we're looking at day tanks, obviously they can be any size or shape, whatever is best to be custom built for the application. And the components on there, we're going to have level control, leak detection, and in many cases, especially for mission critical applications, return pumps are a great idea. Now, from some design standpoints, people would see that a return pump is a potential for fuel being removed from a critical part of the system. But with proper design, proper safeties in place to prevent that, they actually add a lot of functionality to the system and far outweigh any of the downsides. Whether it's to remove fuel that is poor quality or to remove fuel that has been overheated by generator return, they are going to be critical for that as well as testing. So if we have this level sensor here and we're not burning enough fuel with periodic generator testing to allow the fuel level to come down and test the level sensors themselves, this return pump is going to allow us to do that manually on a periodic basis. And we want to make sure with the day tank that we're specifying the number and sizes of the connections. So it's very important that we have these connections on there. Some day tanks will have a proprietary connection or won't have something standard like an NPT fitting. It's important to understand that if these don't have a standard connection, the tank itself may last for a very long time, but the electronics that are hooked up to it, not as long. So we need to keep in mind that for future retrofit, it may be important to have a standardized connection on there. Taking a look at another comparison, we have day tanks versus belly tanks. And if we think about those two pictures that we just saw, the belly tank being the one on the bottom and the day tank on the top. Now with day tanks, you're generally going to have more tappings, more standardized tappings that are going to allow better sensor retrofit, as we mentioned earlier. And it's also going to give you an advantage as far as measuring the fuel in it. So the entire system runs off the level sensor in that day tank, whether it's the transfer pumps or any of the alarms, high and low. And when we have two tanks that are the same volume, but one of them is very shallow and one of them is taller, then the taller tank is going to have better level control. It's going to give us a little more runway on the high and the low and larger space between those level points. Now with the belly tank, obviously there is an advantage because they can typically be packaged with the generator. I've seen many cases where the enclosure itself, the sub-base floor, is the belly tank, or the sub-base tank as it's called. So it can be easy to specify and install, but it can pose a challenge when trying to integrate those level controls that are inside that tank with the existing control system. So we generally recommend that the sensors be provided by the fuel oil controls manufacturer for better integration, because then we know that when startup comes and the two parts of the system are integrated, that those electronics are going to talk to each other and that the signals are going to be what they need to be. Now, what are the day tank instruments that we would typically see? Since this is such an important part of the system, I wanted to take a closer look of those items that are going to be installed in the day tank. And there is a design philosophy difference between the level sensors that we would use on the bulk storage tank and the level sensors that we would use on the day tank. For the bulk storage tank, we're not trying to so much control the level beyond just preventing an overfill. We're merely trying to inventory. So we would use an analog sensor. For the day tank, we're not just trying to determine how many gallons are in there. We are trying to specifically control the amount of fuel in there. So as you can see off to the right, we have a picture of a multi-point level sensor. Now we're not using an analog. An analog is great for determining the exact number of gallons in the tank, but as far as reliability, an analog sensor could possibly malfunction. And typically it's not going to be designed for the total range of the tank. If we have a 3-foot tall day tank, we're going to be using a standardized analog level sensor that could be calibrated for 10 feet originally from the factory. If it was to lose its calibration, now the pump off location or the high level location is going to be feet above the day tank. By using discrete level point sensors, such as the one pictured here where we have 4 floats, typically these are going to be 40% at the bottom, which is low. 50% is the next one up, which is pump on. Then we have pump off is the third one up at approximately 80%, and then 90% is going to be our high alarm. And obviously we can add redundant low and high, etc. to this. That is going to give us level points that are never going to lose calibration. They're never going to move. Each one is permanently fixed at a certain location, and we don't need to worry about them. Now, in an advanced system where the customer also wants to know the exact number of gallons that is stored not only in the main tank but also in the day tanks, we can provide a backup analog sensor to work in conjunction that will just indicate the actual volume of fuel that are in the day tanks. Some other devices that you would see on there are leak detectors as well as RTD probes, as the temperature of the fuel in the day tank is something that's becoming more critical, as we talked about before with generators returning hot fuel, or here in the Northeast with fuel getting cold as well. So being able to tell what the temperature is at each part of the system can be important also. When talking about the day tanks, you may have noticed on some of the previous diagrams of the valves that are at the inlet. Now, if we have a multi-day tank system, of course, we only want to put fuel into the tank that's calling for fuel at that one time. And the way that we do that is with an inlet supply manifold. And this can be as simple as just a single inlet solenoid with a manual bypass, or it can be much more complicated with multiple normally open, normally closed, flow-proofing switches, things like this. At the minimum, we want to make sure that when we have something like an inlet solenoid or multiple solenoids that we have a manual bypass. This is very important for 2 reasons. Number 1, solenoids don't last forever. We want a way to manually bypass around that if there's a malfunction and be able to take out the faulty valve and replace it. Number 2, if we have a situation where we need to manually supply fuel to a day tank, most transfer pump sets that are up to modern standards are going to have some sort of a microprocessor which looks at all the leaks, all the statuses and indications, and then turns on and off based on that. But it will also, if the microprocessor or PLC is down, have a handoff auto switch, which allows the system to bypass that microprocessor and manually turn on the transfer pumps if necessary. Now, in that case, it will not have the automatic operation to open an inlet valve to the specified day tank. It just turns it on and off. So what we would need to do is have the end user open that bypass valve on the day tank that requires fuel to allow fuel to flow into that day tank, and then close it once it's full. Now, a note here on valves that are used in a fuel oil system. On the day tank side, we're typically going to use solenoids. They're fast acting and it's the industry standard. But if we have multiple main tanks, or if we have more than one bulk storage tank, it's important that we use motorized ball valves with end switches. And that's not only for safety reasons, but also for operation. We need to know for sure if we're pulling fuel from one main tank that we're not returning fuel to another main tank, which could cause an overfill. Or worse, if we have fuel being pulled from one main tank, but valves are not open for a return, we now have a problem where our relief valves are not going to work properly. So we need to make sure that if we're dispatching fuel from multiple main tanks, that we're using a slower acting and more robust motorized ball valve with end switches so that we know 100% whether or not those valves are open or closed. Taking a look at leak detection, this is going to be present for the day tanks as well as the main tanks, and it's pretty much going to be required in any sort of double wall tank. There are multiple different kinds. We have many different systems out there, depending if we're talking containment piping or a tank or a sump. And we have leak detectors that can discriminate between the presence of oil or water or even vacuum-based systems. So there's a lot of different options out there, and depending on what kind of system you're using, there may be one that's best for that. Now, the skid that we talked about very early on, that's not part of fuel transfer, but it is critical to the system as far as maintaining the fuel, is our filtration unit or polishing skid. Now, this unit is actually becoming more important as time goes on because we have systems that are larger stored fuel. We have things like ultra low sulfur diesel, which can contribute to long-term fuel storage issues. So these are becoming more and more important. And as I mentioned before, it's not just about filters and strainers. It's also about having a stage like a centrifuge or a coalescing stage where we're actually pulling water droplets out of suspension in the fuel, removing the water from the tank, because the water itself is going to be a major driver of fuel quality issues. All right, we've taken a look at what a traditional system is. We've looked at how to design and size the major components within that. We've taken a closer look at some of the critical components in a fuel oil system. And now I want to take some time to focus on this section, fuel oil system controls. Now we have all this great hardware, all these valves, these tanks, pumps, etc. But the controls are what makes everything work together. So let's take a look. Now, a typical control strategy. You're going to have a control panel likely located at the duplex transfer pump set. It's going to be interacting with the pumps. It's going to be taking a look at those level points in the day tank. It's going to be taking a look at leak detectors, which could be located at the day tank, the main tank, somewhere in containment piping, and many other devices as well. But typically, this is the minimum amount of controls you're going to see for a generator system. While there are a lot of standard pump set control panels out there, it's important for mission critical applications that we take a look at each and every application to make sure that the sequence of operations and the controls are tailored for that specific application. Custom design is going to be key to reliability here. Now, the advantages of modern controls where you have a PLC or a microprocessor is going to be the amount of I/O that you can look at, the amount of functionality, but also the recording of alarms and events. Much of the troubleshooting that we do on a system like this isn't done while the problem occurs. Many times it's done after the fact. And so having a detailed list that's time-stamped with a text indication of exactly what happened and when it happened is going to be crucial to making sure that this system is running in tip-top shape. And a requirement that's becoming almost ubiquitous is that the system is going to interface with a building automation system or a building management system. So having a modern PLC or microprocessor based system is going to allow us to integrate with those much more seamlessly. Taking a look at another comparison, historically we would see a lot of relay based panels, and the functionality worked for what it did, bringing the pumps on and off. They were less expensive, and as far as parts, obviously relays can be purchased at a lot of different sources. But as we mentioned, the detailed error enunciation and recording for PLC and microprocessor panels is going to be almost required for any mission critical application. That, along with the fact that the packages can be UL approved, we're going to have much more visibility so that the person showing up to operate, test, or respond to an alarm is going to get the amount of information that they need immediately. There have been many advancements in fuel system control. So our historical system would have been a relay-based panel. A more modern system would have a microprocessor panel at the duplex pump set. But then pushing on into the future, we have many applications where peer-to-peer communication is also important. So we have an advanced system where the controls are not just located at the transfer pump set, but we have controls located at day tanks, at main tanks, at the polishing skid, and they're going to all talk to each other through a redundant controls network. Now, this offers many advantages, especially with operator interfaces at each location, where if somebody wants to test the functionality of a day tank, they can remotely operate the transfer pump set from that location and see every other location operating simultaneously through a touchscreen or another interface. Here's an example of just one setup where we have multiple day tanks at an upper level communicating with main tanks down below, transfer pump set, we have our connections to the building automation system, and everything is talking to each other. Now, one of the other advantages of this is that since it's operating over a hardened, redundant communication network, all of the wiring for a large system such as this is greatly reduced while increasing redundancy. So we don't need a pair of copper for every level point, for every leak detector. We have our communication lines that can be run and save on all of that infrastructure. Here's an example of some of the screens that we would see for a typical system like this. We would see our main tank starting in top left. Top right, we have our transfer pump set. As you can see in this condition, we have fuel flowing through pump number 2, which is confirmed to be running and being supplied to the system. If we were to go to another tab on the lower left here, we see our day tank. In this case, we have temperature measurement. We can see the state of the inlet solenoid valve. We can see the level of the fuel and where it is as it pertains to the control points. And we can see the state of our return pump. On the lower right, we have another example. As I mentioned, a lot of this can be applicable to a boiler plant, even though that's not the main thrust of this presentation. But here we can see our different boilers, which are calling for fuel. And all of this can be seen throughout the system if we have peer-to-peer communication at different locations. And the advantage of this, anyone who is to respond, they're not merely seeing lights and switches in a certain state, certain lights on, certain lights off. They're able to immediately visually understand what's happening in the system. And if there was a malfunction, they'd be able to see at the bottom where it says no active alarms. That would give them an indication with an actual text alarm saying what is the problem, if there is any, in the system. All right. Well, thank you very much, everybody that took the time to watch and listen to this webinar. I definitely enjoyed presenting it. Again, my name is Alex Canney, and I am here in the Northeast with Preferred Utilities. You can reach us at the numbers shown on your screen or at our website, preferred-mfg.com. We're also on LinkedIn as well, and we try to post some articles and updates on there with some regularity. We also have some webinars that are coming up. In addition to this one, we have ones on fuel oil design in California, out west in our office there, as well as a webinar on the tools that were mentioned in this one, taking a look at some of those resources on our website. And then we have some on combustion as well, as we also do a lot of work on combustion, whether it's high performance, low NOx, anything for your boiler room. And we'll be looking forward to that one upcoming as well. All right, right now we're going to transition to the live Q&A portion of the webinar. And I really look forward to interacting with you folks on the questions that you have, any comments that you have on the content, and we'll talk to you soon. Thank you very much. So thank you very much for your time and attention. We have a couple of phone numbers there, and we have our website at the bottom. I would say that if you need any more resources, our website's a great place to check out. As I mentioned, in the future, we're going to be doing some more webinars on the tools on our website, as well as fuel oil for California. And we have a combustion one coming up for boiler plants as well, which I think is going to be very important. It's a big division of what we do. Anything for a boiler plant and high efficiency, low NOx burners. So if you're interested in that sort of thing, if you like steam, feel free to join us for that. All right, so I'm going to have my marketing guy give me a hand here, and we are going to go get ready for some Q&A.
Hey, Alex.
Yes.
I saw a question in the chat, and looks like it was a private question, so maybe you might not have seen it. But the question was, can you differentiate between which safety devices will come pre-wired with the PLC controller and what is need to be wired into the device?
Sure. Yeah, that's a common question. Just in general, what devices are going to be wired in and what are going to come pre-wired. I will say this. We often try to get as much as possible pre-wired from the factory. Things like inlet solenoid manifolds, we're now doing those at the factory. And the advantage is it's all pre-wired to a junction box, pre-tested. And you can basically, you go from this terminal in the control panel at the pump set to this terminal number in the inlet supply manifold, and you're not just left juggling a bunch of stuff that you don't see very often. That being said, as far as safeties, so as far as wired safeties, I'm thinking of devices like maybe an oil lever gate valve that has a trip switch. So if you have a fire safety valve, which in Boston actually we're seeing less and less of, that may be wired in to our control panel. A lot of the safeties are either on the skid already or are mechanical, like the relief valve doesn't really have an electrical connection, right? I'm trying to think of any other devices. Typically, it's not necessarily a safety, but one of the critical pieces of the puzzle is going to be the flow proving switch. And even though that comes with the pump set, that's typically piped just outside the pump set package. So that'll be a ship loose item. And I see a follow-up here. Leak detectors, level sensors. So as far as those, typically anything on the main tank is going to come ship loose. There are some cases where main tank accessories come pre-wired, but it's extremely rare. So you're going to see leak and level for the main tank. You're going to have some sort of leak detection for the transfer piping. It's very rare now to have a system where we're not at least putting a point leak detector on a riser or on a piping run. Then up at the generator, so it really depends if we have a day tank or a belly tank. So if we have a sub-base tank provided by the generator manufacturer, a lot of the stuff could come ship loose from the fuel oil people. It could come pre-installed by the generator people, and it may need to change a couple of times in the field. That's just the reality of that. And the interesting thing, I will say, it's important to understand not only what devices are typically shipped loose and need to be wired in the field, but you're either, for our system especially, or a lot of those out there, you're going to see either 120 on-off, or you're going to see 4 to 20 analog. So if it's something like a level sensor, analog level sensor on the main tank, that's going to be a 4 to 20 low voltage. That needs to be in a conduit by itself. And then if you have something like a backup high level switch that's an on-off float, typically we'll have that at 120 volts. So that's going to be an aligned voltage run. We outline all of that at the submittal and O&M phases. We have very detailed submittals, which is one of the reasons that, they're not ready the day after we get an order. And then if you ever have any questions on an actual project or a design at any point, we can, whether it's one of us as a salesman or, if we work with somebody in the company, we can get you a wire count, and we can get you, anything specific for a design that you need.
Yeah, something else just to add too, we're expanding our library of Revit files. So I understand for a lot of consulting engineers, that's something that they need. So we've been working with Alex Canney and a lot of our other engineers to provide those to people that need them, the Revit files. So I see another question here, Alex. And I think Tom O'Mara, if you see Tom O'Mara in the chat room, he's a preferred employee, does a very good job with our electrical side. But I saw a question, does Preferred provide detailed drawings for projects? And of course we do. And Alex, if you want to elaborate a little bit more on that.
Yeah, in fact, this morning I was on a job site in Cambridge where we were taking a look at some of our O&M material. We show factory wired devices, we show field wired devices delineated. We, depending on what we're integrating with, we can also, I mean, if it's a requirement for the job at the design phase, or if we're working directly with the contractor or vendor, if it's the case where we need to provide a point-by-point diagram with some third-party equipment, we'll work with you on that. That's not a problem. We can make that happen.
Excellent. If anyone has any more questions, feel free to put them in the chat. And also, like, if you're desiring more information about a certain topic, we could also do a future webinar. I know Alex is very excited to do webinars for you guys. If you guys have questions about, maybe more questions about controls or filtration or something like that. So another question is, assuming UST or AST,
yeah,
what height do you suggest for pipe levels, pickup tubes, return pipe, filtration pipe, and SNR?
Yeah, that's a really great question. So if we're talking, let's say, actually, probably about the same for an underground storage tank or an above ground storage tank. I would suggest for the transfer pump set and for the filtration unit to have completely separate supply lines. You can kind of win in on the return. But the reason I say that is the transfer pump set should have a drop tube that does not go all the way to the bottom of the tank. Typically, we're going to want to see that up a certain percentage. I may have mentioned earlier in the video stream there that we're not going to go all the way to the bottom. Depending on the size of the tank, maybe a few inches, maybe a couple of feet if it's a massive tank. But the filtration unit, we want that to go all the way to the bottom. So that suction drop tube, a lot of times we'll see a contractor we'll cut the end of it at a 45-degree angle and then just basically drop it down in the tank till it hits the striker plate or the bottom of the tank and measure where that is so that we're right at the bottom, because that's where all the water and all the sludge lives. So that's a really good question. We typically want to get that down as far as possible. Yeah. And then for the return, that's a good question. I don't know that I've ever had to actually hit a specific point for a return. I would just say that you'd want that return to still be submerged at low level, because as we mentioned before, anytime you're putting fuel into a tank or pulling fuel out of a tank, we want to make sure we're not foaming. We don't want to be just dropping fuel. And we've had some situations where in a high rise where if we had an overflow, that fuel can get moving by the time it's at the bottom. If we're coming down, a huge high rise, that gravity will really start working on it. So sometimes we'll see people putting like a back pressure regulating valve, something to slow it down, but making sure that it just doesn't fall into that tank, because once the diesel turns to foam, you can't inventory foam, you can't leak detect foam, you can't pump foam, you can't burn foam. It's not great. You got to wait for it to turn back into diesel, which could take a while. So I hope that answered your question, Mark. That's a great question, though.
Yeah, another question that's in the chat is, what's the typical communication protocol provided with your PLC controls or FSC controller?
So we have Modbus on our tank gauge, Modbus on our standard transfer pump set, which is typically the traditional heart of the control system for a fuel oil system like this, and then BACnet as well. It's BACnet IP, so you can just plug in an Ethernet cable on the back end of our 4-inch OIT or 10-inch, depending on the size of the system. So that usually covers us. Once in a while, we run into BACnet MSTP. That can usually be handled with a converter, either on our end or the building automation end. But most of the time, we're going to be covered with either Modbus or BACnet. And if you're seeing any other protocols out there that are becoming more and more common, please throw them in the chat, drop me a line via email. This can also be a two-way street. We love to hear from you guys what you're seeing out there. So, all right. Thank you for that question, Tamara. All right. Well, if there are no other questions, I really appreciate your time. Hopefully everybody is staying healthy during this time, working from home if you can. And feel free to reach out to us anytime via email, phone call. Check us out on LinkedIn. I know we have a ton of posts there. We're trying to do a lot more, especially with people out of the office. So if there's any way we can help you with the design, we're more than happy to.
Yeah, absolutely. And we also have webinars every Thursday for the foreseeable future. Just trying to keep you guys informed about upcoming fuel oil changes and fuel oil systems. Next week, we're going to be doing a webinar about our preferred free online tools and how you can use them to basically design a full fuel oil system. So Alex will actually be giving that one as well. So come back for that one. And in 2 weeks, we have a California fuel oil one. So like Alex said, it's kind of a whole nother ball of wax. So,
and if I could, Michael, I'd also like to promo some point in the future when we're doing one for New York City. So I know, depending on how you feel about that being in the Northeast, it definitely, even though it's in our backyard, it is even more so than California, maybe, as far as regulations and just best design practices. It's going to be really unique. So our guys there, I believe it's John Haber. Is that coming up in a few weeks? Yeah,
correct. We want to kind of work on that in a few weeks, hopefully.
Great. So yeah, we've done one for those in the past, and that's really important. If anybody does any fuel design work in New York City, yeah, you just throw out the rule book as far as the rest of New England. So, all right. Mark is asking if these presentations are available on the website. Are we going to post these on YouTube?
So yeah, Mark, the link that you have to get into the webinar will be, you'll be able to get into a pre-recorded version or a replay version of the webinar. Also, we'll be posting these on our YouTube page. We'll also try to put them on the website so that you can easily link them if you just go to our website. We'll probably put them under the webinar section there for past webinars. So yeah, we'll make these available as much as possible. You can sit them around and send them to your friends and stuff like that, and watch them again.
And I think maybe the one to end on is Mark's question there in the chat channel: is preferred made in America?
Always.
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 That's kind of our thing.
Made in Danbury, Connecticut.
That's right.
USA. So.
All right. Thanks again, everyone. We really appreciate your time. Any questions, let us know.